All right. Let's get started. So, good afternoon, everyone. I am Anshumali Srivastava, founder CEO of ThirdAI. In this room, we have Nick and Jordi, and we have Sid joining from Bangalore. So we have prepared a wonderful next hour, tantalizing you with what we call the next generation AI, scalable, sustainable, and simplified. All right. So let's look at what current AI pipelines look like. So if you go and talk with somebody who is working on, let's say, recommendation engine, versus if you go and talk with somebody working on NLP or let's say tabular classification, they seem to be coming from a different planet. They talk different things, different data pipeline, data processing. They talk different models, different engineering aspects, and even different hardware, right? It depends on what scale people are talking about. And that is how most of the AI current looks like. Remember, they have different feature processing. These tasks are completely different. The code looks completely different. And what we believe that this is something that is not scalable. So essentially, if you have to solve n problems, you need n specialized teams and resources. And from a business leader perspective, this is also an unpredictable return on investment, because let's say if I want to understand, should I incorporate natural language processing into my pipeline? Now, what it entails is first creating those infrastructure, resources, expertise to even build these AI pipelines, models, and subroutines, then plug it in production. And again, like that's a whole different story of an AI model going in production. And in the production, when you test it, you may or may not realize what the value of it, but you have to pay the cost upfront. And that makes this whole process very unpredictable. So currently, the way AI is in most of the systems, it's extremely slow and costly to validate a hypothesis. And our vision of a universal AI, which we think is the next generation AI, is we think about one AI for, let's say, recommendation, NLP, tabular, sequential, and everything. So we believe that there is one simple pipeline, and we are going to show you that what runs on your commodity hardware. So there is no specialized engineering or infrastructure required. And that can solve the problem of recommendation, healthcare, NLP, tabular, and many more. And what essentially it means is that if you have to validate a hypothesis that something works or not, then it is instant, right? I mean, because all you do is you call this one AI, and we'll see in some of our demos what we mean by that. So essentially, this universal AI, you provide a high-level details of what your raw data is. So on the right-hand side here, I am showing you two completely different tasks. One is actually doing NLP text classification, and the other is doing a tabular data sets with timestamp and sequential model. And this is the only code that you need, more or less, to take raw data to a decision. And we'll see more when Jordi will talk about that in the demo and how do we unlock this. So this is more or less what we want to take you. There is no feature engineering required or no hand-holding for the model. The model is trained and ready for deployment. So once this model is trained and it satisfies, the accuracy level, the models will be ready to plug it in form. And the AI will get better if you get more data and more information by itself. And again, like I'll not steal the thunder. This will go more into the demo. So, all right. So this kind of a universal AI seems ideal, but how close are we? So if you look at the trend in machine learning literature, people started with a whole variety of models, transformers, CNNs, and people talked about different architectures for different problems, but they are getting simplified. So I will say the time is right for this kind of a universal AI, because we can think of a one large neural network for all kind of a scenario. And this is what neural scaling laws of the machine learning literature has been pointing towards. Architectures are evolving and they are becoming more or less like each other. And so essentially, if you look at things like GPT-3, DALL-E, there could be one recipe for all, that if you have lots of data and large neural networks, that will give you best accuracy out of the box. But why hasn't it worked? Well, it requires a capability to train and experiment with very large networks and diverse data sets, and very efficient feature engineering. we are talking about a scale of millions to billions of parameters easily on a commodity hardware, so on a commodity CPUs. And to even deal with very large neural networks, the conventional wisdom will say, go think about expensive hardware and engineering. Well, but this is what we at ThirdAI specialize. Our DNA is we can train this very large networks with, on CPUs very efficiently. And again, like I'll not steal the thunder from Nick. Nick is going to give an overview of what the internals of our engine looks like. But right now, this is not accessible to everyone. And I'm glad to tell you that with ThirdAI, we can provide these capabilities and unlock these really large neural networks for anyone. How do we do it? Well, we use something called sparsity, in which we do not use, or we use the computations very smartly and very frugally to give you the best accuracy without breaking the bank in terms of computations and resources. All right, so here's an agenda. Nick is going to give a brief intro for how we are automating AI with really large neural models. Then we'll look at a handful of demos by Jordi. Then Sid is going to talk about how we are rolling our capabilities, and then there will be Q&A. Again, as a logistic purpose, if you have any questions in between, you can still go and type in the Q&A box. And we have moderators who can even answer it live. If there are still questions that are unanswered, you will be given an opportunity to ask in the Q&A questions. With that, I hand it over to Nick.
All right. Hi, everybody. The next thing we're going to do is just do a quick overview of how our AutoML system works and what the different components are, so you can better understand what our models are doing under the hood. At a high level, we think of our AutoML in three components. The first component is your raw data. So this could be tabular data on a file format. It could be something on a cloud bucket, for instance, S3 or the Google Cloud equivalent, or some other format. And then the next part is the streaming feature transformations. In this phase, our models will take your raw data. They will apply a set of transformations to convert it into high-dimensional vectors that can then be ingested by the model. Our models are trained using our Bolt engine, and they can be hundreds of millions to billions of parameters in size, deep neural networks, and they can be trained with just off-the-shelf CPUs. There's no specialized hardware or infrastructure required. So to zoom in on these different components, we can first look at these streaming feature transformations. This is a one-pass streaming algorithm that also exploits whatever parallelism is available. And it looks for several key features that it can identify in the data. The first is just any important elements and features within just the raw data. It'll kind of decide the best way of representing that for the model, and it'll include those in the final representation. The next thing is looking at any semantic relationships. So this could be if you're doing some sort of text classification, you're going to have words and sentences and phrases, and those are going to have a really important semantic meaning to the data and are important for the model to understand. And so our transformations will perform featurization on those kind of semantically intertwined entities, such that you get rich featurizations that the model can extrapolate from. The next thing is temporal relationships. So a lot of data today is time series. So for instance, consider you're trying to you have a streaming service and you want to recommend TV shows or movies. Understanding the history of what a user has watched greatly informs and colors the kind of predictions you would want to give them in the future. For instance, if you know that a user watched the first 3 Harry Potter movies in the last couple of days, then the 4th Harry Potter movie is probably a pretty good guess. Our algorithm will look for those types of temporal relationships, and we'll use that to give more informed predictions from the model. And the final thing is just contextual relationships. And by this, I mean the relationships between different features that are co-occurring in a data sample. For instance, just knowing the age of a user could be useful in giving them a recommendation. But if you also know maybe where they're from, where they're living, you can maybe start to segment the data into more meaningful categories that the model can learn more from. So these one-pass algorithms will look at all of these different types of relationships and features, and will output million-dimensional feature vectors that can then be ingested by the model. So like I said before, our models are trained using Bolt, and there's several key elements of this we want to emphasize. The first is that this is in fact a deep neural network. we're not using tree-based models. And this is extremely important because tree-based models, there's sort of a limit to the performance with the amount of data as you scale with more data. Whereas deep learning and deep neural networks will continue to scale and perform better and better the more data you give them. So we've kind of removed this upper bound on accuracy and performance. The next thing is our models are over-parameterized. So they automatically identify optimal subnetworks for the data set to maximize the accuracy or whatever your metric of interest is. And then finally, like was mentioned before, we use sparsity and adaptive sampling within our models to make sure that the training is extremely efficient and inference is extremely fast. And what this does is that as the model is training, it's using smart algorithms to identify which parts of the network are most important and focusing on computations in those parts of the network. The overall effect here is that you're doing fewer computations, but maintaining the important key elements of the network structure so that the output is unchanged. And this is what makes our inference extremely fast and the training is extremely efficient and able to run on CPUs and not requiring specialized hardware. And the last thing about this model architecture is it's extremely scalable. You can scale to millions of input features, millions of output classes, and this is no problem, even with like billion parameter models, because this adaptive sampling allows the network to grow while still reducing the computational overhead of those additional parameters in size. So next, I'm going to turn it over to Jordy, and he's going to show you some cool demos of what you can do with this. Oh, wait, sorry, I had a summary. So just to kind of do a quick recap, data processing, we use efficient streaming algorithms. We look for a variety of different relationships between features and create million-dimensional output feature vectors. And then we pass it over to the model, which is a deep neural network, scales with more and more data. It's over-parameterized to automatically identify and train optimal subnetworks for data sets. And it uses sparsity for efficient training and inference. And also this type of model is extremely scalable. It can grow to millions of parameters, millions of input dimensions, and millions of output dimensions. Okay, now for real, I will turn it over to Jordy.
Hi, thank you so much, Nick, for handing it over to me. So yeah, thanks so much for coming, everyone. And we talked a bit about the vision of this universal demo, universal AI, and Nick had given a very good explanation about how we leverage deep learning and intelligent transformations on data sets in order to create an easy to use and also very powerful AI model. Now, I am going to dig into the universal part of things, how we're going to package everything into a tool that's really universal. Well, this tool is called the Universal Deep Transformer, because we use deep learning, we transform all the data, and we want this to be a universal tool that can be used for all of your business AI needs. So this is a single API for your business AI needs, and we also commit to providing SOTA performance, state-of-the-art performance, with as little code as possible. Let me elaborate. This means that you can do all of the problems listed here, from intent classification to product matching to anomaly detection, just with a single API, because everything is auto-tuned and the system natively handles heterogeneous data. And with ThirdAI's commitment to scalability, sustainability, and simplified AI, all of our systems don't require any specialized hardware or infrastructure. It also handles millions or more unique input and output categories without blowing up in memory, something that can't be said about all platforms. Finally, we still commit to around 1 millisecond latency for all of our inferences, and we also provide explainability. So in addition to the things that ThirdAI always promises, we are currently improving in the universal aspect of things, the simplicity aspect of things, through auto-tuning and handling all this different sorts of data. What does this actually enable, though? This enables us to rapidly prototype and experiment. Going back to what Anshu said before about how sometimes it's really hard to know what to do, how to use AI in your business, because even just a prototype requires a lot of effort, a lot of engineers, a lot of engineering time, not to mention you have to deploy it and you don't even know whether something will work. So by having a universal tool that you can easily configure to do whatever problem you want to solve, then suddenly you can do all of this very quickly, very rapidly. And we're going to demonstrate that today with some real examples. The first one I want to cover is intent classification. I provided some random samples from the data set that we're going to use. And the gist of this problem is you have a text query, for example, how would you say fly in Italian? And you're supposed to figure out what the intention is behind this text query. For example, in this case, that is a request for translation. Now, why would anyone want to do something like this? Without a system like this, what you would have to do is, suppose you have a customer service center, and a customer contacts your hotline and says, hey, I want to do something. Not all of your agents are well suited to answer that request, so you would have to route the customer to the right agent, to the expert for that request. In the best case, you would have to go through an operator, wait for an operator to be available, and then have that operator route you to someone else who knows that problem better. In the worst case, you might have to go through several hoops, several operators in order to get to the person you actually want, which can be a frustrating experience for users. With an intent classification model and a route and a system to automatically route your customer calls to the right agents for that intention, you can just have a system in place of those operators, which means that, first of all, it's cheaper because now you don't have to pay more people to route these calls. And instead, maybe you can even allocate a larger part of your workforce to the experts who actually handle these requests. And secondly, your customer doesn't have to wait for operators to be idle anymore in order to get their requests routed. So it can create a more instantaneous and overall more pleasant experience for the customers. And research has shown that satisfied customers lead to better consumer loyalty and, of course, just a healthier business in general. So now that we've covered why you would want to solve something like this, we're going to see how we can use UDT to build an AI solution for this exact problem. Okay, so here you can see this is just a Python script where you can you can instruct UDT to solve this problem for you. As you can see, the constructor is very short. You only have to pass in two objects. The first one is data types, the second one is target. This data types is where you would specify the columns of your data set. In this case, we mentioned how we have a text column and a categorical column. So you just have to pass in bolt.types.text and bolt.types.categorical. And then finally, you want to specify the target column, basically what UDT is supposed to predict. And just like that, you have defined your first UDT model and built and prototyped a solution for this problem. The rest of the script is just for training and configuration, training and evaluation. And let's run this now to see how well we do. All right. Oh boy, sorry, that's a blunder. All right. So as you can see, we were in just a few seconds, we were able to prototype, we were able to build an entirely new solution, a solution from scratch for this problem. And we got a very respectable accuracy too of around 91%, which is close to state of the art. And one thing I wanted you to notice here is that we have a latency of only 0.1 millisecond, which is way under the millisecond guarantee that we give you. So yeah, not only do I want you to pay attention to how easy it is to develop a solution and prototype with UDT, also want to bring your attention to how quickly we were able to train this solution. And also, all of this is running on a commodity CPU machine, because that's what we commit to. We never want people to need specialized hardware to run any of our things. So we solved one problem, right? Big deal. Well, this generalizes to other text classification problems too. Let's say you get reviews on your website and you want to know which ones are more urgent to respond to. Then you can use a text classification solution like this. Let's say you want to match customer queries on your search engine to the matching product category. You can also build something like this. by just specifying, just mapping queries, text queries to the appropriate categories. The next problem that I want to demonstrate is a situation where your data has a lot of features. So imagine you want to know whether there is some anomalous behavior on your e-commerce website or whatever online service you have. You have information about their location, their session length, what they've been doing, and you want to know whether it's some shady behavior or not. So in general, this means that you have a lot of columns, a lot of features. Maybe you have some categorical features. Maybe you have some numerical features. Maybe you have some text features. How can you handle that? Can our solution handle this wide variety of problems as well? Well, the answer is yes, and I'm going to show you just in a bit. I'm going to show you how easy it is to transition from that simple text model that we had into a more comprehensive model that can use heterogeneous forms of data. So yeah, I just want you to see how similar they are. All you have to do is to change the data type of the data set that you have. In this case, let's first use only 4 columns of our data set. We have a numerical column. We also have some categorical columns. All right, we were able to quickly train this model, and we're getting around 80% accuracy. What if we want to use more information though? Let's say we actually were able to collect even more information, more observations. Can we scale the model to include those as well? The answer is yes. The answer is yes. And all you have to do again is to just add more of these data types, and the model will handle that for you automatically. So let's do that now. All right, just a couple seconds, we were able to train this model, and now we have a much better accuracy of almost 86%. Again, a state-of-the-art number for this data set. And once again, I want to show you that we were able to stick to a very fast inference with a latency of barely 0.15 milliseconds. So through this demo, I hope that I was able to show you how easy it is to use more information. The minute you get more observations, you can instantly prototype with UDT, include that information, and see whether that actually helps your business or not. Not only does this work for the data set that we had before, this generalizes to all sorts of tabular classification problems, which is quite ubiquitous in industry. So things like fraud detection, anomaly detection, even for medical use cases as well, a lot of people usually use a tabular data set format. Now, the final problem that I want to show you, and I think this is the most exciting, is personalized recommendation. It's this idea that you give each user an experience based on who they are. If you have an anime buff who has spent the last 2 weeks watching the 2 longest shows in history, you probably want to recommend them another anime show. If you have someone who just finished watching the first 2 installments of a great trilogy, you probably want to recommend the 3rd one, right? So it's this idea that I'm going to give you an experience that is just the best for you instead of just a generic one that I give to everyone. But why would a business care about this? Well, there has been a lot of research that shows customers want this. Customers want this, and that not having something like this can really prevent customers from staying loyal to your business. In other words, it's almost a necessity in this day and age. Why wouldn't you do this then? It's because it's complicated. Take this as an example. Usually the data that you actually get is this kind of sequence, like time series sequence of observations. User A bought item B at timestamp C. And then you have like a couple, you have different rows that each have the same user, and then they buy different items. And then you have to transform all of this into this other data format where each user, where you have the user and then all the things that they bought in a clean sequence like that, in order for machine learning pipelines or like machine learning systems to understand what you're doing. So yeah, you have to integrate these complicated transformations to your machine learning pipeline. And just to show you that this is actually a big deal, here's example code. This is around, I think, 300-ish lines of code only for the time series part. It doesn't perform this transformation in a streaming fashion, and this is only for the time series part of the transformation, not handling all the other categorical numerical text features. So it is a big deal. And the thing is, we don't even know if this will help. As Anshu said earlier, this really aligns with what Anshu said earlier about how difficult it is to quickly develop and rapidly experiment with your hypotheses to really get what really helps your business. Because you don't, like, what if you spend all this time building these pipelines and turns out it doesn't even help? Well, we want to solve that problem as well. And through this demo, we want to show you how simple it is to use time series or sequential information with UDT. Before that, I want to talk about like what the data set looks like. So the example on the left here is very much like the data set that we're going to look at. We have a sequence of interactions between users and items. And the problem we're looking at is what we want to do is to predict the next thing that the user will interact with. Let me go back a little bit. The data set that we're going to use is a movie recommendation data set. So imagine something like Netflix, right? A user watches something, you want to predict the next thing that they watch. And that is a very difficult problem. That is a very difficult problem because you have so many things to choose from. How do you predict the next one that a user will watch, right? So in order to do that, really, you can't, it seems to me like you can't just look at all the things that the user has watched. You have to look at the recent things that the user has watched in order to make a very informed decision on what the user is going to watch next. So let's just jump into the demo. Like before, we just defined the types that we have in our data set. We have the user ID, we have the movie ID, as well as the timestamp. We trained this beforehand, and we're getting these numbers, which seems kind of low. But if you think about it, there are 3,000 movies to choose from here. It's really difficult to find out what a user is going to watch next. In fact, if you compare this with the state-of-the-art two-tower model, you're going to get about the same performance. And we tested this. You're going to get the same performance if you are unable to keep track of what the user has just watched and their recent behavior. Now, I'm going to show you how we can make use of temporal features of the recent interactions that a user has with UDT. If you try to spot the difference is here. It's just this line. That's all you have to do in order to track in this case, the last few movies that a user has watched. Everything is auto-tuned. All you have to do is that you want to track the movies that a user has watched in this object. We also ran this beforehand. And if you notice in the recall at 10 number, we were able to improve our performance by 8 times. We were able to improve it by 8 times, and we're still able to run all of this with a latency of just 1 millisecond with just one line, right? So this is something I'm really excited about personally, just because of how much less time you need to spend now in order to experiment with this kind of thing and see whether it actually helps. Just one line for 8 times better predictions. And you might, and we also tested this on a different data set, this time a larger data set. This is the Netflix data set where you want to recommend the next movie out of 17,000 movies. We compared this with a TensorFlow two-tower model, and we were able to get 24 times better performance and precision at 1. One thing that I also want to point out here is, as Nicholas has said before, we really commit to scalability. So even if you have millions of movies to predict from, that won't be a problem for us due to the sparse architecture that we use. And again, this is not something that can be said about all frameworks, but that's something that we can handle. Not only can you do movie recommendations, you can also generalize this to all sorts of other time series and sequential problems like demand forecasting. Or maybe if you have a travel tourism company, then you can also recommend travel and tourism based on the things they've enjoyed in the past. So this really broadens the types of problems that we can solve with UDT. To wrap it up, I want to ask, why should we care? Well, we should care because, hey, we just spent a few minutes to build solutions for real world problems. Think about how much more you can do given more time. We were able to, in the truest sense, rapidly prototype with just a few lines of code. And this is important because many more business problems need AI solutions. We only covered 3, but there are a lot more that you probably know better. Your business probably has other needs that we can solve with AI. So this allows us to build more, use more data, and test more rapidly, because this is the only way that we're able to get measurable benefits out of AI. So once again, I want to wrap this up and remind you that we have this package called the Universal Deep Transformer. It's a single API for all of your business AI needs, and we give you state-of-the-art performance with very little code. And that means you're able to do all of this with just that one API, all auto-tuned, handles all sorts of handles heterogeneous data from categorical to numerical to time series data types, and even text as well. And just as our other offerings, you don't need specialized hardware or infrastructure. It can handle millions or more unique input and output categories. It's very, very fast. And we also have an explainability API. That pretty much wraps up the demo session. I'd like to pass this over to Sid to talk about how we're rolling this out.
Hey, thanks, Jordi. So hope you guys are excited to see how you can use this in production. I just want to point out a few things. So all our training infrastructure is in Python runtime. So you just need to have your simple Python runtime to train our system, any model, and it can be done on any commodity CPU. You don't need any expensive hardware. For inference, we support Python and Java. Apart from that, we do distributed training for very large data sets. So even for billions of data points, if you want to train it really, really fast, we do support distributed training. Apart from that, the best part of our capability is every UDT model is production ready. You don't need to do any pruning, quantization, or distillation. You just need to train it, plug it, and use it in production. The other part is you can integrate it easily with your code base as a library on your on-prem systems or any cloud offering. So if you guys are interested in trying it out, reach out to us at contact@thirdai.com.